All right, so let me start by writing something you already know. So this is, and let me also write my email where you can, reach me with any questions related to these lectures or otherwise. So my job is to introduce conformal field theories and the conformal bootstrap, and this will happen over the course of, many hours. So it will be, maybe a slow process, but this process should be, everybody should stay along with the progress along the way. Sometimes you watch a movie and they abduct someone, they put a hood over their head, they throw them in the car and they take them somewhere, right? And then they tell them, here you are. I don't want the lecture to be like this, I don't want you to feel like you've been abducted with a hood pulled over your head and then I say, this is the bootstrap, and then you say, how the hell did we get here? Okay? So I want it to be much more, gradual, and I want to make sure that everybody keeps pace with how things are going, and that requires you to ask questions, which I hope you will do. And I cannot commit to providing the correct answer to every question, but thankfully we have other experts in the room. Hopefully they will keep coming. They can offer their answers or corrections. So this is the first remark. The second one is that unavoidably, I will not be able to explain everything in great detail because things would take forever in that way. So it's not a good policy in life to trust anyone, but I will ask you to trust me at certain points, but that's not an invitation for you to then stop thinking about what I said and just trust me. It's an invitation to think about it, and if you find it problematic or you can't really, see how it goes, to then discuss with other people here, your classmates, and also discuss with other experts that are lurking around, and with me, of course. So these are sort of like the general, this is the general framework in which we will be operating, and hopefully it will be fruitful for everyone. Everybody will get something out of it. Okay, good. So to start with the introduction to conformal field theory, we have to motivate a little bit why conformal field theory is important. And for that, perhaps the best way to do it for a mixed audience of high energy and condensed matter people is to discuss phase transitions, which are deformations of matter lead to different phases. Now, deformations of matter here, it may mean deformations due to temperature, or maybe due to pressure, where you squeeze something in a certain way. But such deformations of matter, in general, lead to different phases, and there are many familiar examples of this. Perhaps the most familiar one is the boiling of water. Where we have a liquid phase that goes into a gaseous phase through heating up. And you have all seen in your education the phase diagram of water. It's the pressure and temperature diagram, where we have something that looks like this. These are the so-called coexistence curves or lines of first-order phase transition. And here we have the solid phase, here we have the gaseous phase, and here we have the liquid phase. And this is the triple point of water, where some pressure and temperature conditions are such that all three phases coexist. And then there is the line of first order transitions where solid goes into liquid, that's ice melting. And then there is a line of transitions where liquid goes to gas, that's water boiling. And then this line goes on forever, but this line does not. This line terminates at this point, which we call the critical point of water. And at that point, there is no more any distinction between a liquid and a gas. So if you look at you can go to YouTube and search, critical point of water, and you'll find these experiments where at some fixed volume, people heat up some substance, not necessarily water. The easiest one to do is CO2. Anyway, you heat it up, and then you see that you have the liquid phase and the gaseous phase on top with a clear phase boundary. And as you heat it up at the right pressure and temperature, you see that the individuality of the two phases completely disappears. And there is no more two phases. Up here, all we have is the supercritical phase of water, which is sort of like something in between. There is no distinction between a liquid and a gas. And that first happens at the critical point. Now, at the critical point, there are various symmetries that emerge, and we will be talking about them as we go along in this course. One that is very important is that the system becomes scale invariant. In other words, the phase of the system, correlations of the individual degrees of freedom spread over large distances. They are not confined to small interactions with their nearest neighbors. They are spread out over the whole system. And we'll see what that means as we go through the course. And at the critical point, there is an important characteristic that you can find literally thousands of substances that have such critical points. And they can be made out of very different things. However, you can find thousands of substances that have critical points, and the physics at those critical points is exactly the same, no matter what substance you're looking at. Away from the critical points, it's not at all the same, but at the critical points, a certain universality emerges. And the way the system behaves is universal across literally thousands of substances. And so this definitely gives you a very good reason why you want to study critical points. It's a point of universal physics, and understanding it is, you have a chance to understand with one theory, say, the behavior of thousands of different physical systems. So that's very appealing from a theoretical point of view. An example of this universal behavior is the heat capacity of water, which goes like it happens to diverge as we approach this critical temperature with a certain exponent, typically denoted by alpha in the literature. And alpha is not a number we can compute exactly, but we can determine it in experiments, and we can compute it theoretically as well. To a certain extent, we know it. It takes this value, but we don't know much about, what is perhaps an analytic expression for this value or anything like that. We just know it as a number that we know a few digits of it, but we don't really know for this case of, say, water at the critical point, what this number actually is. If it's rational, we don't know any details about it. So this is very appealing theoretically, and it turns out that it also encompasses two very basic ideas of how we think about nature. And these two very basic ideas is the ideas of symmetry and scale. So it is a very general observation that nature is organized by symmetry and scale. And this comes in all areas in pretty much all areas of physics. And it's kind of amazing that just by thinking about how water boils, you get such general principles of physics right. The symmetry principle was first described in this context by Landau, who said that different phases of matter are characterized by symmetry. So, for example, a solid is not the same as a liquid because in the solid phase, you have broken some rotational and translational symmetries because you have an underlying lattice that broke those symmetries. So the solid lattice breaks symmetries. For example, translations. A liquid does not. While if you look at a liquid and a gas, well, they don't have any really different symmetries. It's not like one breaks a symmetry and the other doesn't. And this goes back to being able to move from a liquid into a gas without crossing a line of transitions, because you could move by playing with pressure and temperature so that you follow a path like this, where you go around the critical point and you never cross a line of first-order phase transitions. Okay? So if you want to characterize phases of matter, you have one option is to characterize them by the symmetries they have. And this applies rather universally, and of course is not complete. There are phases of matter that do not have this kind of description, but we will not discuss these. Then the other part of how nature is organized is scale, and this was first discussed by people like Wilson, Kadanoff, and others, where the critical observation is that little things affect big things, but not much bigger things. In other words, little things affect big things, but are slightly a little bigger than them, and then those affect things slightly bigger than them. And this, the way these relationships go, they go sort of gradually. It's not that something very small will affect something very big without going through these intermediate steps of affecting its next bigger thing, and so on and so forth. The mathematical formalism for this is called the Renaultization Group. And we will discuss a little bit about what that is today. Okay? But at this point, it is very important that these two, and I'm repeating this point because it's very important, just thinking about how water boils and how we approach this critical point is enough to give us a lot of information about more general systems in nature, and in general how nature behaves, and how we can characterize phases of matter, but also phases of quantum field theories, phases of all sorts of things, generalized, and the principles used in all cases are the same. Symmetry and scale that you can see here in this simple system. Okay? Any questions about this? Okay. Okay, so after this general and qualitative discussion, we're going to introduce the first example where we can see these ideas in practice. And that's the Ising model. Okay. So what is the Ising model? I mean, you all know probably what it is, but let me introduce it anyway. We choose a lattice in d dimensions with n sides. So here we make no assumptions about what d is, but we will make an assumption about what n is. N will be something very large, okay? But of course, you can define the model with any number of sides, but we will assume that this n is very large in our discussion. And this lattice can be any kind of lattice, but we will typically take it to be something regular, like a square lattice in 2 dimensions, or a cubic lattice in 3 dimensions, or a hypercubic lattice in any other dimension, but it doesn't have to be that, right? And on each lattice side, we introduce a degree of freedom that we will call a spin, although it has nothing to do with a quantum mechanical spin. We just call it a spin because it takes 2 values, up and down, or +1 and -1. So for each lattice side, which we will label by I, which goes from 1 through n, we have a discrete variable we will call it Si, which can be +1 or -1. Okay? And I will refer to this as spin, but it's not like there are any commutation relations or anything like that. It's just a name. Okay? There is no quantum mechanics at all here. Okay. Now we will have a certain energy that we will write down. There's going to be perhaps a magnetic field, B, which we will couple to the sum of all the spins. And then we will introduce a certain coupling between nearest neighbors. It's a quadratic coupling, and the coupling constant is J between nearest neighbors SISJ. So in a cubic lattice, this will only be, you choose any point, and it will be only the neighbors of closest distance to that point that you sum over. Okay, very good. This J over here, since these variables S take only + or -1 values, if we want to lower the energy, and we want spins to align to lower the energy, like we do in the ferromagnetic case, then this sign will be a plus. In order to get the minus sign here, J should be positive, and this is the ferromagnetic case. If the spins anti-align to lower the energy, which is the antiferromagnetic case, then we're going to get a -1 from here. To kill it, we need another minus from this J, so the negative J case is the antiferromagnetic case. Okay? So the sign of J will tell us if we are in a ferromagnetic or an antiferromagnetic, or if the ferromagnetic or antiferromagnetic arrangement of the spins is preferred to minimize the energy. Now this is a situation at 0 temperature, right? But we want to understand temperature dependence. And now we see that there is a certain tension, because when we introduce temperature, we see that there is sort of a new kind of effect coming in. When we introduce temperature, there is the magnetic field wants to align the spins in order to lower the energy. J wants to align them as well. But, you know, in its own way. But when you have temperature, you no longer care about the energy, you care about the free energy, right? So when you have temperature, what you go is from the energy to the free energy, which is the energy minus temperature times the entropy. And it's much more efficient to raise the entropy in order to make the free energy small than to try to minimize this at non-zero temperature. And obviously, a configuration of spins that is aligned has zero entropy, but one that is completely random has maximal entropy, and therefore temperature wants to have spins pointing in all sorts of different directions, right? So, so here we want to maximize S, the entropy, which means that, you know, spins point randomly. So we have two quantities, two interactions, two types of terms that want to align spins and one that wants to mess up the alignment. So now we have this tension. And this is where all the fun is going to come out of. Okay, so of course at non-zero temperature, when we want to start computing physical quantities, we need to introduce the partition function. Which here, I will write like this. So sum over the set of spins, e to the minus beta. I use e, so let's just use e. Where this beta is just 1 over the temperature, okay? This is our partition function. And in this example of the Ising model, what we will be interested in is the magnetization which we will denote by M. And this is supposed to be the average value let me write it like this, some sort of average value over the sum of the spins. We will call this the magnetization. And it is a quantity that can take values between -1 and 1, right? In terms of the partition function, if you go through the standard manipulations, this turns out to be equal to 1 over n beta d log z dB. For the specific E that is given here, okay? Okay, very good. So now we know what to do. The object we're interested in, M, is given in terms of the partition function, so all we have to do is compute the partition function and we're done, right? But of course, this is not easy to do. There are known solutions for this particular model for the partition function only in d equal 1 and d equal 2. And beyond that, we do not have any way, any known way to compute the partition function. That doesn't mean it's not computable, but we just don't know how to do it. So since we don't know how to do it, we will start to develop various approximations and ways to deal with it. And this will be what we do next. So this is hopefully very familiar, but if there are any questions, again, don't be afraid to interrupt. Okay. So if you look at what we did, we started with some model and we gave it some energy over there. And then we said, what we're going to do is we're going to sum over the spins. We're going to care about this magnetization quantity. And then we're going to compute this partition function, which also sums over all the spins. So the partition function is not a function of the spins anymore. It loses all the information about the spins, but it's a function of whatever other parameters you had in your model. In this case, this B, that J, and the temperature, right? So we went from a very microscopic description of the model in terms of the energy to a very different description in terms of the partition function, which only involves macroscopic information, quantities like the temperature, the magnetic field, and this coupling J. And it turns out that progress in finding ways to analyze a system, progress can be made by seeking something sort of in between, where in terms of going directly from this very finely grained prescription of the energy to this very coarsely grained prescription of the partition function, we introduce sort of something in between, okay? So how do we do this? How do we do this? First, we start by identifying a quantity that we're interested in. And in this case of the Ising model, we want to understand the physics of magnetization, how magnetization behaves. And this is going to be this is going to be the quantity we focus on from now on. We're not going to talk about individual spins. We're going to talk about the magnetization associated with a given configuration of spins. Now, this is not a unique association. It's not like that one configuration of spins has a unique magnetization, and no other configuration has that same magnetization. Many spin configurations can have the same magnetization. So this is sort of a coarse graining of the information in the system. We go from individual spins and this very finely grained understanding of the system to sort of a little bit more of a, coarsely grained quantity that we care about, the magnetization. Good, so that's step number one. So if you want, in the language of constructing effective theories, we identify the relevant degrees of freedom first, and then we try to write down the theory that those degrees of freedom participate in. So this is what we are doing. As I said before, the magnetization is a variable that goes between -1 and 1. Okay? And then the partition function, we will assert, so this is an assertion, that we can get to the same partition function by doing that sum, but also by doing another sum, the sum over magnetizations of phi to the minus beta f of m, where we sort of assume that for every magnetization that we're summing over in this sum, we've done some other sum over all the individual spin configurations that lead to that same magnetization. Okay? And then we're going to say, well, there is lots of spins here. This n is supposed to be very large, right? And I know that this is really a discrete variable, right? But because we have so many spins, the spacing is very, very small between these discrete values of this variable. So then we're going to say, well, why not just treat it as continuous, right? So we're going to substitute this sum over here for an integral between -1 and 1 of dm e to the minus beta f of m. And we're going to make our life easier this way. It's easier to do integrals than to do sums, although we will do neither. Okay. So this is the logic that we use to construct the effective field theory, the effective free energy, maybe, that is associated to the Ising model. We don't know what this f of m is, but so far we have motivated that there exists an f of m, knowing which will be equivalent to knowing all the information we want, because we would then do this integral and we would reproduce this thing that we asserted is the same as the partition function up there. Now there are various, logical steps here that seem reasonable but require a lot of mathematical justification. We will not go through any of that. But presumably, this all looks well-defined and kosher. We didn't do anything really crazy for a physicist. Okay? Good. So where do we go from here? So we call this f of m, typically give it a name. People call it the effective free energy. Okay, good. Of course, it's not a function just of m, right? It's a function also of these parameters b, j, and m, which is the magnetization. Okay. It's also, by the way, it's also a function of the temperature. So it's not like in quantum mechanics, when we do, say, a path integral, we take the action, which has no h or anything like that, and then we stick it into the path integral, and the h is like this beta here. Here, it's not quite like this. The f of m also has beta in it. So it's not quite the same, but it sort of looks similar in some sense, although this m over here is a variable that does not have spatial dependence at this point. So this is not really a path integral. It will become one very soon. But it's the important subtlety between this thermal stuff and the quantum stuff is that this beta appears also inside the f. Okay. Okay, so let's keep going. So the question now has become, how do we compute this f? Yes? Yes. We will make various assumptions about it in a little bit. It will be a continuous function, analytic function of m, but yeah, we will talk about the assumptions in a little bit, yeah. Thanks. Okay, so the first thing people do once they get to this point is they say, well, how do you compute this f? I don't know how to compute it, but let's make an approximation called the mean field approximation. Now, this is a very bad name because the mean field approximation means that there is an approximation you can improve on, but it's not. It's not an approximation because it's not like once you make it, you can then fix it order by order in some sense. But anyway, that's what people call it. And what they do they go back to that energy that I just erased, I guess, and they say, well, instead of summing over the spins, I'm just going to sum over the magnetizations. Okay? Let's just do that. And so my energy will become sum over Im minus j sum over m squared in some suitably defined sense. And then you are going to get some factors of n from these sums. And from this equation over here, when you do the sums, you can define the energy per spin, which is going to be minus. Remember, this magnetization is just the same magnetization. The sum over I will give you just a factor of n that we just put over to the other side. And then here, you will get minus 1/2 jq m squared. You're going to get the n as well. Q here is the number of nearest neighbors. And the number of nearest neighbors depends on the dimension you're in, is a function of the dimension, right? But we're going to call it Q. Now you can do the sum and compute this free energy, effective free energy per unit spin, where you just divide by n. And this turns out to be a computation you can just do. You can stick it into the integral, and the computation you can do, and it turns out to be of this. The answer turns out to be of this form. And this is your first calculation of this free energy. And now at equilibrium, where you're looking at for the minimum of this F, you can find what your magnetization actually is. So at equilibrium, you have, which gives you this well-known condition that the magnetization is the hyperbolic tangent of beta times B effective, where B effective is B plus JQM. So this, M appears both here and inside here, so this is a complicated equation to solve, but this is the magnetization at equilibrium when you make the assumption of the mean field approximation. Now, this is sort of an easy way that people use to compute the free energy, and it gives you nice expressions for what this object looks like. But of course, it relies on the initial approximation that we made, that it's proportional, that instead of summing over the spins in the energy, we're just going to sum over the magnetizations, assuming the same magnetization for every configuration of spins in some sense. So we have this mean field approximation. Now, this is the starting point for Landau theory. So in Landau theory, you say, of course, the mean field approximation is not to be taken seriously, but the whole logic with which we have approached this, this problem should be taken seriously. And so we have identified this effective free energy per unit spin, F of m, that we want to calculate. We can't really calculate it unless we make some approximations that maybe we don't want to make, but maybe we can approximate it. Maybe it's a function of this single variable m. The other parameters appear in there, but they're just parameters. Maybe we can just expand it. We don't know what it is, but maybe we can expand it. Now, if you took the mean field approximation answer here, you can take this and just expand it. So you're going to get minus Bm. You're going to get this term over here, but at the quadratic level, you will also get another contribution, and you're going to get in the end T minus JQ m squared. This is what you're going to get at the quadratic level. So this is still using the mean field approximation and the exact answer we found there. And then you are going to get 1 over 12 T m to the 4. And if you keep expanding, this is what you're going to see. There is also a constant term here, but I will neglect it because it's not important for what we want to say. Constant meaning M independent. Okay, so now let's make the following assumption. Let's suppose that B is 0. Let's suppose we don't have any magnetic field, and we are just looking at the effects of the temperature versus the ordering of the spins associated with their coupling J. Now, we'll also drop all these other terms because we will make some sort of assumption that the magnetization is small, and we will then drop all the higher terms. And then we notice that the coefficient here does not have a fixed sign. So there are two qualitatively different situations. If you were to plot this f of m as a function of m, there are two situations. If this coefficient is positive, then this is obviously positive, just like this, with 0 at its minimum, right? This is a situation if T, the temperature, is bigger than JQ. Okay. But if this T minus JQ is negative, then at small enough m, it's going to win because this is to the 4th power. And so it's going to be smaller than the m squared power. But then eventually this is positive, so it's going to win and it's going to come back up, right? And since this is an even function of m, you're going to get the same situation on the other side too. So now, things look different. This is smooth over here. Instead of having the global minimum of this function being at m equal to 0 for t bigger than jq, for t less than jq, what you have is two different degenerate minima at some specific non-zero values of m, and the m equals 0 solution became a local maximum of the function. And this is what you may, if this was a scalar potential in field theory, you would call this the case of spontaneous symmetry breaking, where you go from a situation where you have a global minimum to the situation where your system has to now choose between two different, inequivalent, but of the same energy minima. The choice going from this minimum to this minimum corresponds with basically flipping all the spins in the original description, right? If they all point up, it's an equivalent energy state than if they all point down, as if they're all pointing down. It's equivalent in energy, but they are, of course, different states. Okay, so the vacua are inequivalent. Nevertheless, the energy is the same. Okay. So, okay, what do we do with this? First of all, we're going to call this JQ the critical temperature, denoted by TC. Okay. If you were to look at the magnetization in this situation as a function of this TC, so here's your TC, and before, there are two states for the system. There is one state where the magnetization, you start at +1, and it goes down like this, or the state where you start at -1, and it goes up, and then at T larger than TC, there is only one state for the system where the magnetization is 0 at equilibrium. Okay? This is a phase transition. This is exactly like that phase transition we had for the critical point of water, where you had two different phases and they were separated for a certain range of pressures and temperatures. Here they are also separated for a certain range of temperatures. But you reach a point where they are not separated anymore, and there aren't anymore two distinct phases. They merge into one phase. Okay? So this is exactly what was happening when we had the case of water, and it turns out, in fact, that in 3 dimensions, the universality classes associated with these two phases are actually exactly the same. They have the same critical exponents, although one is a system of molecules of water interacting, and the other one is a system of spins on a lattice. Okay? which is a consequence of this idea of universality that we discussed. So again, here we have a phase transition, and to set some notation, the m equals 0 state, we call it disordered, and the m other than 0 state, we call it ordered, referring to the underlying spins. In one case, in the ordered case, they all point up or they all point down, so that it's ordered. In the other case, the temperature has 1 and the system is completely disordered. Everything points randomly in whatever direction. Okay, so this is Landau theory, and we don't have time for Landau-Ginsburg theory, but we can talk about this after the break. Any questions? Okay, it's all completely known, I guess. Okay, then we can have a break, and we'll resume at 11. So we just finished off with Landau theory, where instead of trying to compute this free energy, this effective free energy per unit spin, we said we'll approximate it instead. So now, after Landau proposed this, and the possibility of this different phases related spontaneous symmetry breaking of some sort was realized, and the next step was a paper with Ginsburg. It should be perhaps called Ginsburg-Landau theory, but a lot of people call it Landau-Ginsburg theory because it originates from the ideas of Landau, and then Ginsburg came along. Anyway, where they said, well, why treat this magnetization as a global quantity? Maybe, if we have this lattice of spins, maybe we should give it an x dependence. Depending on where you are on the lattice, you imagine that you, so let's draw it here. So you have a lattice, so this is supposed to be many sides, okay? Not just the few that I will draw. And instead of thinking of the magnetization as a globally defined quantity, you might think of sort of like clusters inside this lattice, where you're going to treat this sort of as a subsystem. You will assign a magnetization to this, which is now going to be a function of where this is on this lattice. And there's going to be, a different one down here. And since there's going to be some x prime, some other position, this function will not take the same values for this sublattice than this. Now, we assume that we have a large number of sites and that each of these clusters that we make has a large number of sites in it as well. And we also assume that there is a large number of these clusters. Okay? So everything is large. This is sort of how you might imagine assigning x dependence to this variable that we call the magnetization. And formally, you may write something like the magnetization as a function of x is 1 over the number of spins in some box that you define this way times the sum over I of the spins inside that box. So what happens now? Well, the integral that we had before for the partition function will now become a functional integral. We're going to have to integrate now over all these functions of x. We will not make, of course, precise what this means, but it will be like, exactly like a path integral in quantum field theory, again with the same caveat that this f also depends on beta. Okay. Okay, once you make this a function of x, now we see the first signs of a field theory, right? Now we'll call this thing m of x a field. It gives you a number for every position that you give it. So it's a field, and doing this path integral is equivalent to solving, we assert is equivalent to solving the theory. But of course we cannot do this path integral, so what can we do instead? Now comes the time to think physically about what properties this f of m of x should satisfy and impose them and see how much mileage we can get out of these properties. So the first property of is locality, where we imagine that whatever interactions exist in that lattice are such that, you know, the spins can talk only to nearby spins. It's not like one spin can talk to a very, very, very far away spin with some interaction term. Eventually they will talk because everything, you know, talks to their nearest neighbors and they talk to their nearest neighbors, but the interactions happen locally, and of course they spread globally, but they happen locally. So this is the assumption of locality that we will have, and this allows us to write this f as some integral of some other quantity, which is a local function of m, which depends, so this quantity over here depends on m, depends on the derivatives of m, and so on. But it doesn't depend in a non-local way in this quantity. There is no like 1 over box m. There is no, there are no things that violate locality of this quantity as a function of m. Okay, so this is the assumption of locality. Higher derivatives, of course, can appear here, not just the first derivative, but higher derivatives can also appear. Okay. Now, another assumption is that whatever lattice you put on this system, if you imagine the continuum limit, there will be some symmetries that emerge in the continuum limit. In particular, in the continuum limit, you will get perhaps rotation invariance and translation invariance. So what we will do is we will demand that those are symmetries of this f of m. So we'll demand translation and rotation invariance. And these are symmetries that will emerge in the continuum limit. We will also demand that we have a Z2 symmetry, which, because of the underlying configuration of spins that we have in mind, if you took a configuration of spins pointing in some way and you reversed every spin, you're going to get basically the same energy back. So this means that if the magnetization goes to minus the magnetization, and if you have a magnetic field, that should go also to minus the magnetic field, then you should recover the same theory. So the theory described by this f should be Z2 symmetric. Obviously, this means that you cannot have the power, say, m cubed appearing inside this expansion of this Z. And another assumption is the assumption of analyticity. Because what we will also demand of this function is that it is an analytic function of m and its derivatives and so on. Finally, we will also sort of give an order to the strength of these terms. We will also say that fluctuations happen over large distances. Fluctuations in m happen over large distances, and therefore derivatives of m become smaller and smaller the more you take. So that the size of the one derivative term is bigger in some sense than that of the second derivative, of the third derivative, and so on. So we will introduce a certain ordering in the derivatives. And using all these assumptions, some of them might be better motivated and more general than others, but using all of them, we will again imagine expanding out, expanding this f. So we will write it as integral. So let me write it like this. So there is some quantity that depends on temperature. So we're going to have the first derivative of this m squared, because we cannot have by Z2 symmetry, for example, we cannot have something that is linear in m or third power. We also have to have rotation invariance, so we have to do something with this vector, so we have to contract it with some other vector, and we're going to take that to be again the derivative. So all these assumptions are implemented in writing what the form of this free energy is, and then we have various coefficients that we introduce, alpha 2, alpha 4, which depend on temperature, that will be the coefficients in the expansion of this quantity. We will not be able to derive an exact expression for this quantity, because that would require us to have a way to perform manipulations to get this quantity exactly like we did in the mean field theory way. But without the mean field theory approximation, we cannot compute it exactly, but we can still postulate that it has a certain expansion consistent with a bunch of properties that we demanded based on physical principles. So this is basically going from Landau theory to Landau Ginsburg theory, amounts to replacing the magnetization with a local variable m, and we go basically to a field theory description of the system. Okay, any questions about this? Good.
How analyticity is a physical requirement?
Sorry?
How analyticity is a physical requirement?
Well, we don't want this to have like 1 over m squared. We don't want it to have terms that are pathological like that. We don't want the free energy to blow up in configurations of spins that, have close to zero magnetization, for example. I don't know if there is another, other experts in the field might have, but I think this is the basic physical assumption. We want things to be weighted similarly. We don't want magnetization that's close to zero to lead to some divergence. Yep. And the same with derivatives. We don't want if a derivative go to zero, then that we get another divergence. We don't want that. Yep.
I was going to ask the same thing for higher derivatives.
Yeah. We don't want them to appear in denominators.
Okay, what about now, higher derivatives? Because you gave an explanation for higher derivatives.
Yeah, they will all be there. They will all be there. Here in the ... you will have the second derivative of m appearing, third derivative, all of them will appear in this expansion. This is a completely general expansion of a function that satisfies some of these properties, but is otherwise completely general and does not have any reason to terminate. It's a full series expansion. However, we're going to make the extra assumption, which I didn't write here, and maybe I should have, like we're going to say that somehow the derivative of m is much, much smaller than the second derivative of m, which is much, much smaller than the third derivative of m, and so on. We will make the assumption that the systems we will be dealing with exhibit fluctuations, but those fluctuations spread over large distances smoothly so that their derivatives behave in this hierarchical way. this is an assumption. Not every function, of course, have to behave this way. But because of the local interactions, we imagine that this is a good approximation to the way the system, the interaction in the system spread.
Do you mean another sign?
Sorry?
You mean the second derivative?
Sorry, yeah, I meant the other way. Sorry, thank you. Yeah, thanks. Yeah.
You assume anything about the coefficients besides that they are functions of t? Or no?
At this point, I don't assume anything about the coefficients. I don't assume anything about the coefficients. Yep.
Can you have cross terms with m and gradient?
Sorry, can you say it again?
Can you have cross terms where you have m and derivative of m or some terms like that? Cross terms with m and
as long as you preserve translation rotation invariance, you can. But for example, there will be a term like, I don't know, m squared del m squared. But there will not be a term m del m, because then you cannot preserve rotation invariance. There was a comment, I think.
It is easy to exclude negative powers of m, but fractional powers, like square root of m, it's not so easy. But I think the logic is the following, that if you think about deriving this, you fix configuration of m, and then you integrate out everything else around this configuration. So if you are able to select and m includes all your soft modes, then the rest fluctuations are kind of gapped, and they produce only analytic terms in m. This is kind of logic. But this is the most subtle assumption of this Landau theory, of course.
Thank you. Yeah, that's a very good comment. And thank you for that. Yeah. Okay, yes. So there are various subtleties and there are various assumptions here. And analyticity is, of course, a rather subtle one. So definitely feel free to discuss this more. But within these assumptions, let's now keep going. And the first thing we're going to do is, instead of writing m, so this is an m of x, let's rename m of x. We'll just call it phi of x from now on. This will bring us closer to the language of field theory as we might know it. But it's the same quantity, right? I didn't change anything. Okay, so the moment we have a description of our system in terms of some sort of path integral with a certain, action, if you want, in this case, it's this effective free energy we've been discussing, we want to start to compute correlation functions, okay? We want, for example, to compute the correlation function between two field configurations, two magnetizations. Remember, we have this picture up there. We want to know what is the probability, in some sense, to have those two configurations this distance apart in the lattice. So this will be this given by this two-point function. And as you know, there are many two-point functions to consider. There is the disconnected, there is disconnected, there is all these different correlation functions we will discuss. Here, we will be interested in the connected. The connected two-point function, okay? And in order to understand how to compute this, what you have to do is go back to this path integral picture and make some assumption. Perhaps you make the assumption that there is no terms beyond m squared, so that this becomes a Gaussian integral. And then in order to compute that integral, you go to momentum space, you manipulate things there in the various modes that you introduce for the scalar field. So this is standard quantum field theory computations of this kind of thing. And then you end up with a certain expression in terms of functional derivatives of the logarithm of the partition function for what these correlation functions are, right? So if you recall all these steps, this will become equal to 1 over beta squared times this functional derivative. Where here, in order to do this computation, what I have done is I have terminated, let me write it down, I have written the function f of phi of x, terminated at the quadratic level. So this is just and I introduced a source. So I renamed some coefficients. Now I'll just call it gamma, and this I will call mu squared. And I introduced a source for this field phi. And now standard manipulations in the computations of correlation functions in terms of path integrals will tell me that this two-point function, the connected one, is going to be given by this functional derivative with respect to the source. Okay? Very good. And let me give this a name. We'll call this 1 over beta times the Green's function g of x minus y. Okay. So this is the object we want to compute to understand correlations, how correlations behave in the system. Okay, so let's set y equals 0. You can use your translation invariance in this two-point function to move this configuration to the point y equal to 0. And also, let's define some quantity called xi, which is root gamma over mu. We'll see what that is later. Then, following the standard manipulations that I described, where you take your field phi, you expand it in momentum modes, and then you make sense of the path integral in momentum space, and then you Fourier transform back into position space, you will find an expression for this g of x, the two-point function, which is equal to just g of the magnitude of x, and this you can already expect from rotational invariance, right? And then this is equal to 1 over gamma Okay, so this is the expression that we have for the two-point function. Starting with the theory, of course, where we have neglected all terms higher than quadratic, okay? Or maybe I shouldn't erase this. Okay. So how do you compute this? We want to compute this, and the way to do it is to use a trick. If you want to compute this integral over here, what you do is you say, I'm going to rewrite this 1 over k squared plus 1 over c squared using a certain integral representation, which goes like this. This is sometimes in high energy physics called the Schwinger trick, but I'm sure in condensed matter it has some other name and by some other person, so I don't want to give it a name. So this is what you do, and then you stick it in there for the denominator, and then you interchange the order of the two integrals that you have. And in this case, g of r becomes, so you have your 1 over gamma, integral from 0 to infinity dt, then you have your k integral, and now you have this exponential and the exponential e to the minus ikx, and what you notice is that this is linear in k, this is quadratic in k, and you can sort of complete the square, right? between these two exponentials. And it turns out that you can write it like this. And then you have the terms you added in order to complete the square. Over here. So this is, I didn't do anything, I just rewrote things at this point. And now you can do the integral over k, because it's just quadratic in the exponential, and you are left with another integral over t. And then if you look at this and you go back to the books, you see that this is what's called proportional to what's called the modified Bessel function of the second kind. It's just some special function. The answer turns out to be, if I did the calculation right, is this. So this is the two-point function in position space. Okay? Now this is not very illuminating, okay? It's not a prerequisite to know how the Bessel function behaves, but in order to understand then how it behaves, we have to look at it in different limits. And it turns out to behave very differently. So this expression over here behaves very differently depending on the limit you take. So if you consider the limit where the distance of the two clusters that we were looking at is much smaller than this characteristic distance xi, then you get one answer. The answer looks like, I will not write the overall coefficient, 1 over r to the d minus 2. And this is valid only if the distance of the clusters is much, much smaller than the characteristic distance given by xi. If the characteristic distance is much, much larger than the one given by xi, you get a very different looking result. So this is the behavior of the two-point function as a function of the distance of the clusters. And we see that if the clusters are relatively close together, as defined by the characteristic length scale xi, then you get a power law. But if they are very, very far apart, the interactions between them go down by an exponential here. And you also have this power law in the denominator. There is a fundamental difference, therefore, in the way the two-point function behaves. This quantity xi, this characteristic length, we call it the correlation length. And it gives us sort of a distance, a natural distance below and above which interactions behave spread in a very different way. And since when we introduced xi, it was proportional to 1 over mu, and mu is going to, like when we did the approximation, the mean field approximation, this mu was proportional to T minus Tc, right? Remember, we had critical temperature was JQ, and mu was proportional to T minus Tc. Xi, because of its dependence on mu, will go like 1 over T minus Tc. Okay? And this, in this picture, which is again the mean field approximation picture in some sense, because we have neglected, it's the free theory, we have neglected all the higher order interactions, and we have only taken the theory at the quadratic level. We get a certain length, the correlation length, that diverges with the distance from the critical temperature with a certain power law, with coefficient 1. Now, in a conformal field theory, or at the critical point, what happens is that this correlation length obviously diverges. And then all distances are smaller, much smaller than the correlation length. Oh, sorry, yes, you're right, 1/2. Thank you. The correlation length, when you approach a critical point, where t becomes equal to tc, will diverge, then every distance will be much smaller than the diverged correlation length, and you will get this behavior at critical points for the correlation function of the magnetizations for the different clusters that we define. And as we will see, this is the characteristic behavior of correlation functions in conformal field theories and scale invariant field theories that we'll start discussing tomorrow. In general, when you add interactions, what happens is instead of getting this 1 over r to the d minus 2, you're going to start getting corrections to what this exponent is, and those corrections are related to things called anomalous dimensions of operators and so on. But we'll discuss that starting tomorrow in the day. Well, maybe if we get to it today. Any questions? Okay, similarly, you can, of course, evaluate further correlation functions in this free theory. Everything can be computed, and there will be, again, behaviors like this, and whenever the correlation length diverges, you go to a critical point, there will be very simple power law behaviors of various correlation functions you can compute until you get to high enough points where things again start to become complicated. Yeah.
I don't understand how you're getting that relation for correlation length that by mod t minus tc, because I thought that that was root gamma over mu, but
yeah, so I basically used from before that this mu squared from before was going like, so I guess I have erased it, but mu was going like, mu squared was going like t minus tc. From when we worked out the Landau theory, we had two contributions to the quadratic term. One was coming from this JQ that then became the critical temperature, and the other one was coming from the expansion in M of the other part with the logs of the free energy, right? And so this mu squared behaved like t minus tc in Landau theory, so I basically extended this to this theory as well, and then put it into the definition of Xi. Okay, so this is we got to basically to understand the behavior of correlation functions in Landau-Ginsburg theory, assuming no interactions, which is very good. And now we want to understand something more about these parameters that I introduced up there. So when I wrote down this free energy, I said, okay, here are some parameters, gamma of t, alpha 2, alpha 4, but I didn't really say what those are. They just appeared there as expansion parameters, right? But now we want to understand a little bit more about what those parameters might be. And doing that, to do that, we have to discuss the renormalization group. So let me rewrite with some new notation this f of phi here. Maybe like this, m mu. So what I've done here is I have rescaled the field phi to eliminate the parameter gamma. And since I'm imagining doing the path integral over this field phi, it doesn't matter if I change what I call it, right? So I can call phi prime to be phi times root gamma, and it should still be okay. So this is just some rescaling of the field. And then I have renamed some parameters. Here I call this quadratic parameter mu squared, and the quartic one I call it g, just some coupling g. And this I don't assume to terminate this expansion. I'm going to carry it, through all the way, compute terms order by order in the field phi as we go along. Now, we have to ask the following question. At what scale is this free energy describing our system? We called it an effective free energy, and we said, oh, we're going to take clusters of spins, right? And we're going to look at quantities defined for those clusters, m of x, in the Landau-Ginsburg theory. But then we never specified how closely we are looking at the system as observers, right? Are these clusters very small? Can I use sort of a microscope and look even closer and see them as bigger? What is the resolution that I, as an experimentalist or as an observer, have over this system of spins? Now, it is conceivable that the theory I will write down will depend on how fine a resolution I can get to, right? And I have not quantified this at all in this discussion. And in order to do this, we have to discuss ideas of the Renaultization Group. Now, what does it mean, how finely grained can I look at the system? It's not an observer-dependent thing, but it's more a statement about what scale of physics am I interested in. If my experiment or my computation is only concerned with physics that only is sensitive to modes below a certain energy scale, then it makes no sense for me to even be discussing energy modes above that scale, because I'm not sensitive to them. They are completely fixed. They are not dynamical. I only can talk about dynamical computations for energy scales that I can resolve, that my question is actually asking. It doesn't make any sense, to be asking questions at energy scales that you cannot resolve. Then the answer, you're insensitive to the answer. So the idea of the Normalization Group is then to say that the scale at which we observe the system has a relevance to the physics questions that we can ask, and the effective field theory that we write down depends on the scale at which we observe the system. How it depends on that scale is what we will discuss now. Okay? So, suppose we care about physics up to a length scale L. Suppose this is a certain length scale that beyond which we cannot resolve. For L smaller than this, we cannot resolve the system. So we want to write an effective field theory that is valid up to that length scale in some sense, but beyond that we are completely unaware of what it might look like. Now notice that I never mentioned anything about scales so far, right? So you might think, well, this should just apply the way you wrote it down. I mean, you didn't mention anything about scales. And in a sense, it does. But we'll see that there is a little bit of a difference due to the Renaultization Group. So how do we do this? Well, we know how to do it. You say that in the same picture where we were calculating, substituting for phi of x, we were substituting we were writing it as, sorry, let's write it the other way around. We were introducing the modes of the field phi, which depend on a specific momentum, as the Fourier transforms of the fields in X space. what we can, instead of working in position space, what we can equivalently do is say, well, our theory, our experimental abilities rather, can only resolve modes up to a certain cutoff. We will call it lambda. For any k with magnitude larger than that cutoff, we cannot, we're not sensitive to it. And therefore, this cutoff defines the point beyond which our theory we don't expect to make sense because we have no way to verify it beyond that cutoff. Okay. So we will basically take k and we'll say we will only consider k's that are less than 1 over the length scale that we introduced before, which is like a cutoff lambda. And this sort of makes sense as well from the lattice point of view because we did have a lattice to begin with, right? So we don't expect anyway to be able for our theory to make sense all the way up to infinite energies, which means 0 length scale separations. Because if it did, then we'd reach the lattice spacing, but we couldn't keep going beyond that because the lattice spacing is a fundamental cutoff that you have in your theory. So if you want, you can think of this lambda also as the lattice spacing of your original lattice model. Okay. Good, so okay, so what we're basically saying is that the momentum modes associated with the field, the phi k's, are 0 for k's that are bigger than lambda. We cannot excite such modes in our experiment, therefore they are frozen to 0 for any momentum with magnitude bigger than lambda. But now you can ask the question, well, what if there was another cutoff smaller than lambda, let's call it lambda prime. Suppose there is a lambda prime smaller than lambda, and our theory stayed below both, our experiment was below both lambda prime and lambda. Then is there any difference between the theory I would define at lambda prime and the theory at lambda? Our low energy experiment, which is below both of these, will be the same, will give the same answer. But as far as the theory is defined at the scales lambda prime and lambda, are they any different at all, or are they exactly the same? Okay, so let's call this, let's call this lambda prime lambda over zeta, where zeta is less than 1. Sorry, more than 1. So the concrete question is, I define my theory at lambda, okay? I can do computations with that theory and compute my low energy effects. Above lambda, my momentum modes are frozen to 0. Equivalently, I could have defined my theory at the lower scale, lambda prime, and again, use that theory to do my computations, right? But what theory do I use then? If lambda prime is less than lambda, do I use the same theory as the one at lambda, or do I use a different theory? And how might it be different? So this is the fundamental question of the renormalization group. And the way, until what time do we have? 5 more minutes, okay. And because I never used any other arguments than the properties I outlined here before to write down that effective free energy, it turns out that there is no freedom in the expansion. The only freedom is in the coefficients. So the expansion that I did in this field phi must remain the same because of some other function, but it's still the expansion of that function around phi equal to 0, and it's going to remain exactly the same. The coefficients might change, and the way the coefficients change is they pick up a zeta dependence, so that the theory you write down at scale lambda the coefficients depend actually on lambda, and the theory you write down at scale lambda prime, they also depend on lambda prime, which is lambda over zeta, and therefore they pick up a dependence on this parameter zeta, which allows you to talk about flows in the space of theories as parameterized by these coefficients. Now, there is a well-defined way to do this, and the well-defined way is, what we call the Wilsonian Renormalization Group, where you imagine integrating out momentum shells of this field. So you go to your field phi k, and you write it as phi k plus phi k minus, and these are modes of high and low energy, or UV and IR modes. And what you imagine doing is that you want to describe your theory only using the phi k minus modes, the low energy modes that are there, even below lambda prime. These modes over here have a part that is there below lambda prime, that is there also between lambda and lambda prime. And what you do is you integrate out the k plus modes. If you want a more specific description of what these modes look like, phi k plus is equal to phi k for k and is equal to 0 otherwise. So this is the high energy part, if you want, of your field phi. While this over here is so this is how you split your field. And then your theory, and then in order to implement the renormalization group, what you have to do is you integrate out these high energy modes, and this will allow you to write down a theory valid at scale lambda prime and below. The old theory is valid at scale lambda and below. In order to compare the two theories, what you have to do is then say, well, one of my theories is valid at scale lambda and below, the other one is at scale lambda prime and below. I cannot compare them as they are. I have to bring them both to the same scale. So what you then do is you rescale the momenta of the theory valid below lambda prime by the same factor of zeta that you had. So now you bring them both up to the same scale, and then you compare them at that scale. Since we used, as I said before, the most general expansion, what that means is that you are going to get a difference in those coefficients, and those coefficients of the theory at the scale lambda prime will be related to the coefficients of the theory at the scale lambda through what we call a renormalization group flow. Okay? And this is the only effect that can be there between the two theories defined as scaled lambda and lambda prime. So just to summarize this, the normalization group tells you to do the following. You integrate out high K modes. Then you rescale momenta so that you bring the theories back up to the same cutoff. And when you rescale the momenta, of course, the coefficient in front of the phi term will also pick up a new coefficient dependence. You also rescale that to keep the field normalized to the same value of 1/2 in the front. Again, here rescale fields. Appropriately. And in this way, the result of this is that coefficients in the expansions RG flow, meaning that they pick up a dependence on the scale at which you define your theory, lambda or lambda prime, and this scale turns out to be described, the evolution of the coupling constants in the theory turns out to be described by quantities called beta functions. And those beta functions can be computed, well, in most cases not exactly, but the moment you turn on all those interaction terms, beta functions can be computed order by order in perturbation theory, in that parameter G, for example. And it turns out that fixed points of those beta functions, the zeros of those beta functions, correspond exactly to points where the correlation length again diverges, and those are the same points where we pick up conformal invariance and we reach a critical point. So there is this endpoint, if you want. So let's draw it here. This dependence of the couplings on the scale may terminate so that you have some ultraviolet theory up here, and this theory, as defined by the parameters in the expansion we were discussing, but then those parameters change under RG flow, then you go to the infrared, and the question is what happens in the infrared. Now it might be that these parameters, I don't know, go off to infinity and do crazy things, or it might be that they end up at a point where their value is fixed again. Such a point is, again, we call this a fixed point, but it turns out to be equivalent to the critical point that we were discussing earlier. And in order to motivate this equivalence, it's not easy. I mean, I don't know that there is a proof that this equivalence works. In order to do it, you have to invoke ideas of symmetry, universality, these kinds of things we've been discussing. But in the end, fixed points of these beta functions turn out to correspond to critical points, and quantities you compute with perturbative methods or conformal bootstrap methods that we will get to correspond to critical points in statistical physics systems that we've been describing today. So this is more or less all I wanted to say today. Well, not exactly, but more or less. So we can stop here and continue with this tomorrow.